are ice cubes.
They are, but they're molecules.
Cool. So as you can see here, this is ice cubes, but they're actually molecules.
Like a solid molecules.
Yep.
Molecules.
Yep. And as you can see here, we're going to melt them again. How?
By leaving it outside, right?
Yep. Let's go. Eat. By the way, I went to Burger King. Yep. Anyway, was this potential? I mean, how's it? Potential Spaniard.
Hey, during the lesson?
I'm trying. Oh,
Yeah.
never mind. I'm supposed to do them actually outside. Like, dang. Whoa. 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 So now, I got the ice cubes. And now we wait for the epic moment. Yeah. I could have sworn I just saw a dinosaur. Wait.
Off topic.
No. Oh. That reminded me of Monica.
Stating clearly presents
That wasn't
a molecule. Though textbook definitions of the word molecule can sometimes be a bit complicated, a molecule can be loosely thought of as a group of atoms stuck together, usually through chemical bonds. Here we see a single hydrogen atom traveling through the cosmos. It's made of one positively charged proton in its nucleus and one negatively charged electron. If our lone hydrogen atom happens to pass close enough to another lone hydrogen atom, their electrons, which are attracted like magnets to protons, can pull the atoms toward each other until they collide and stick together. The two atoms now share each other's electrons in what is called a covalent chemical bond. What were once two individual hydrogen atoms have now formed a single hydrogen molecule. This bond is not permanent. With enough heat or due to interactions with other molecules, the hydrogen atoms will readily separate once more.
Yeah, where'd they
Different
go?
types of atoms can form different numbers of chemical bonds. A hydrogen atom can only form one covalent bond at a time. If a third hydrogen atom were to collide with a hydrogen molecule, it would simply bounce off, or if it hits hard enough or in just the right place, it can trade spots with one of the existing atoms. An oxygen atom can typically form two bonds. A carbon atom can make four. An argon atom won't usually bond with anything. Even though possible bond numbers per atom are pretty small, huge molecules
What the
can form.
frick?
For example, even though hydrogen can only form one,
You're
it's made of
missing out.
3 atoms. This is possible
No,
because
I'm not
oxygen,
missing out.
which can form 2 bonds,
Yeah.
forms just 1 bond with each hydrogen atom. A single molecule of the sugar known as glucose is made of 24 atoms, a special arrangement of carbons, hydrogens, and oxygens. A typical fatty acid in the human body may vary in length.
What the
This one
frick?
here,
Fatty
and finally, a
acid?
single protein, depending on the
What?
type, can contain over 500,000 atoms all covalently bound together.
Did
The
you
molecular
just say
models that I've been showing are space-filling models. They show us roughly what the outside of each atom's electron cloud looks like, and different types of atoms have been assigned different colors. When we look at real molecules with a scanning tunneling microscope, they look pretty similar to these space-filling models, but the
Well,
atoms
you
are
know,
not
it could
color-coded
look
and
more
their edges are fuzzy. That
like
blur
a
is
movie
partly due to the
or
microscope's
something.
limitations, and partly because atoms actually do have soft boundaries. When looking at complex molecules, space-filling models, and especially actual images of real molecules, can be a bit confusing to look at. which atoms are bound together, which atoms are just close to one another. For this reason, chemists sometimes use what are called ball and stick
Guys,
models.
it's melting.
These highlight the bonds between atoms,
Is
the
it melting?
skeleton of a molecule, instead of
Dang.
showing each atom's outside surface. In 2009, Dr. Leo
Let's see if
Groves
it's,
and his
oh
team
my
at
god, it's
IBM
actually
discovered a
melting.
way
So
to
that's
take
two
actually symmetrical
atoms
pictures
together
of
collide
My
into
hand
solid.
is water.
This is
Yeah.
not a
They're gonna
computer-generated
collide
model.
into
This
one.
is an actual scan of a real
Dang, we're going to
molecule.
collide into one
Amazingly,
single
atomic
ice
theory was
cube from
allowing scientists to
BFDI.
draw molecules
Two,
with
no, they're
surprising
going to
accuracy
two
more than
atom,
100
which
years
is two
before
ice
this image
Slash
was
cube.
finally
molecule.
taken.
They are
That's quite a
molecule, but they're
testament
two
to
ice
what
cube.
scientific
What
thinking
happened?
can do.
Ice cube.
When atoms come together
What
to form a
happened?
They
molecule,
become
the
one
molecule
ice cube.
vibrates
No,
between its
liquid.
bonds in a regular
Oh, they
pattern.
become
You
water
can
to
think of the bond
drink.
as a bouncing
They will
spring.
collide and become
This is because
liquid.
the protons and the nucleus
Dang.
of each atom
I
repel one
don't know
another,
that I
while the
could
shared
melt.
electrons in each bond pull the atoms back together. The vibrations we find in molecules are the result of a perpetual tug of war between these two forces. If you add more energy to a molecule with heat or light, the amplitude, the length of each vibration will increase without changing how frequently each vibration completes its cycle. This means the bouncing spring stretches further and the atoms move faster. If you add enough energy, the bond will eventually break. Scientists are fascinated by molecular movements and want to understand them better. These vibrations have a huge number of potential applications in chemistry, medicine, electronics, and computer engineering. Watchmakers, for example, use the unchanging speed of molecular vibrations to build watches that keep nearly perfect time. In a quartz crystal, bond vibrations between its atoms resonate, causing the entire crystal, when cut to the right size and shape, to oscillate microscopically at 32,768 times per second. Inside each quartz watch is a tiny crystal along with electronics that can count the crystal's vibrations. This then tells the second hand precisely when to move. In April 2019, in the journal Nature, Junhee Lee and his colleagues from the Center for Chemistry at the Space-Time Limit
It's
have
melting.
published the first images ever taken of molecular vibrations at the atomic scale. Though these images may seem a bit strange to you and I, they show
Nice.
researchers exactly how this molecule bends and pulses between its bonds. Scientists can use images like this to build accurate models predicting exactly how different molecules will behave under various
Did you
conditions.
see this?
With this new precision knowledge, engineers are working on solar panels that
Mhm,
generate
it's
far more
melting,
energy
colliding.
than
X
computer
ice
chips
cube. I'm
that
just
do
kidding.
not
I'm not
overheat.
shipping super
And
big ice
researchers
cube
are
because
planning to
they're
use
the
this
same.
imaging technology to better understand our own DNA. Even in a field as thoroughly studied as chemistry, the old saying is still true. Somewhere, something incredible is waiting to be known. So in summary, what is a molecule? A molecule can be described as a group of atoms stuck together through chemical
Still going.
bonds. Different types of atoms can form different numbers of bonds. Molecules can be as small as two atoms.
So what
stuck
did he say
together,
about
or,
what is
as
molecules?
the caseful, is waiting to be known.
Okay.
So
They
in
will ask you
summary,
what's molecule?
what is a
What's
molecule?
molecule?
A molecule can be
Molecule?
described as a group of atoms stuck together.
Is a group
through
of atoms
chemical
stuck
bonds.
together.
Different types of atoms
These
can
ice
form
cubes
different numbers
will
of bonds.
soon
Molecules can be
be
as small
a
as two
few
atoms stuck
with
together,
ice
or, as is the
cube.
case
They
for
come
some
with the
proteins,
never. Okay,
they
stop.
may contain over 500,000 atoms, all covalently bound together. Recent advances in molecular imaging are now letting us take snapshots of molecular vibrations at the atomic scale. I'm John Perry, and that is a molecule stated clearly.
Stated clearly.
Okay, now put.
This animation is part of an intro
Mom?
to chemistry series.
Look. It's becoming water.
Yes, it's colliding together.
Colliding. It's colliding.
Yes, it's definitely colliding together.
Like, sorry.
It's like
Sorry.
two atoms
Sorry.
colliding together.
Sorry.
No problem.
Let's see that again.
Hey, you're going to wet your book, you know? Okay. Alright, so. Here. My son. Now clean up your hand. This is wet. All right.
Is that wet?
No, that's just quotation.
Cool.
All right. All right, now that we've seen, so that's the second day experiment. So how do you explain?
They're obviously colliding. That's how I also know they're colliding.
Make sure that you write it neat, okay? So we can read it.
Okay.
Thank you. All right, my dear. They're colliding.
Look. It's becoming water to drink. This is probably going to be the new way we make water. Wait, is it?
No, that's the new way to preserve cold water.
So, does that mean this is the new way to make cold water?
Let's say that you go somewhere, you can drink your ice after it melts. So you can probably preserve it.
So, is this how you make cold water, though?
Mm-hmm.
And after it melts into cold water and there's no more ice cubes, just cold water.
Just cold water. And after you leave it in the heat, it's just going to evaporate.
Well, is it going to be able to be drinkable?
After the heat, and if it's gone, no. Because it will be up in the air.
But after it's melted and there's no more ice cubes and it's only cold water. So after it melts into just cold water, is
You can
it
eat it.
drinkable?
It becomes liquid water. Liquid matter.
A liquid matter?
So you
So
can
it's
drink
safe
that.
to drink? Epic.
If it is water, something you can drink.
Well, is it water right now?
Yeah, but now you put your hands in it, you clean up, you can't drink it.
Okay. Wait, it's working.
Okay. I know that we're not fan of the cold thing.
You know what? Not even gonna fix that. This time I won't. Just for one time, or maybe something kind. I don't even know.
Okay.
I mean, maybe just for her something. I just don't know. Ugh. Just
Happen?
for one- I mean, just for something time only. So explain what you think is happening to the molecules inside of the liquid. Sorry.
Okay.
Sorry.
No problem.
Becoming water. Cold water. Actually, I mean
Liquid?
becoming cold water.
Oh.
Yeah.
Write it clearly, okay? Because I can't read that. And nobody else if I take a picture.
Cool.
So make sure you write it neat.
Cool. Mm.
Neat. Neatly. Properly, papier.
Period.
When you're tired
Okay, we're
and
on
when
to
you're
our-
not, it's
Okay,
completely two
we're
different.
on to our last question for the school day today.
Okay.
That is, explain how you think the liquid turns into gas. You take I'm just kidding. Simple. You boil the freaking water. I mean, you
Yeah.
boil the water.
And evaporates.
Yeah, but I'm just gonna write down boil water. You know how it goes. Boil. I mean, boils. Okay then. boil or boiling. I change my mind even if I
See
even
how
said
you
it.
write that one?
But I
It's so
did not
beautiful.
say it. I'm just gonna write down boiling. I mean, boiling. If I even say it,
Oh my God,
water.
keep your writing like that.
even if I even said it or didn't say it,
Oh my Lord. Look at that.
still bad.
No,
Period.
it's beautiful.
Still bad. I mean, like, look at it. Like, do you
Okay.
not see the E?
I like this
Like,
bad one than this one.
look
So
at
I
it.
want you to keep this one. Okay, this one is nice.
I mean, do you not see the E? Like, look at it.
It's okay. That's like even grown-ups write like that.
Okay.
It's beautiful. So
It's
I
only
want
good
this.
for adults, but not for kids like me.
Kids like you can write beautifully like this, Dagmar. Keep up. This is the way.
Yeah, kids can, but not me. Everyone can, but not me.
I see. Okay, can you continue writing like this for the
I
future?
mean, like, look how you write. Hey, your writing is like so beautiful. Oh, I wish I can like put it in a hall of art or something.
The same here. With this writing, I can put it in a nice museum.
Maybe you shouldn't do that. How about you put your beautiful handwriting and your beautiful arts in a in an art hall.
Okay, so let's put our own beautiful handwritings into our museum.
How about we just make an art hall in this house and we can put your beautiful arts and everyone's beautiful art
Thank you.
in the art
Okay.
hall.
Okay, we'll do that. In the meantime, are you gonna keep this handwriting?
Yes.
Thank you.
Yes, I'm gonna keep my bad handwriting.
All right, we're done for today.
Thank you.
You're welcome.